In the previous lecture, this is where we left, but an important note, you need to remember what histogram is and what density based estimators are. If I just open up that very quickly. So when I just look at this histogram figure, I just looking at figure. Now, once I generate this is the regular histogram. I can determine where the data is more populated easily based on this histogram. So I can say that this area is the most populated one, right? Because of this is higher. But when I go for h is equal to 1, this area this region is the most populated region. And this is the least populated region. There is nothing in this area. Similarly, this area, when I go h is equal to 0.5, this area is more populated, and this area is more populated than the other areas. So by just looking at it, I can easily see. For naive estimator, it's almost the same. So this area seems to be more populated than others. Here in this case, again, this region seems to be more populated than others. And then here is even more detailed. This area, this region, and this area is more populated. So you can see where the most populated data appear in the list. This gives a quick view. Let's come back to today. So I started talking about this Minkowski distance. So it's the generalization of the Euclidean distance. R is a parameter provided by you. If R is equal to 1, it is Manhattan's developed distance for L1 norm. If R is equal to 2, it becomes Euclidean distance. And for R is equal to or infinity, it is minimum or L maximum. I believe you should be able to compute what L1 norm and L2 norm. Basically, for example, if you look at these two data points, P1 and P2, with values XY values 1 and 6, 4 and 2. For L1 norm, you take the difference of each attribute value, take the absolute value, and add them up. For 1 minus 4 absolute value, and 6 minus 3 absolute value, you get 2. For Euclidean distance, you take the difference and take the square of the differences, 1 minus 4 squared, plus 6 minus 2 squared, and then take the square root again and take 5. One thing that's not always clear is L max or L infinity norm. What you see is for each attribute, you find the difference in absolute value. So 1 minus 4 is 3 in absolute value, and 6 minus 2 is 4. You pick the difference that is highest. So 4 is higher than 3. That's why L infinity norm becomes 4 in this case. You pick the attribute that has the highest difference in absolute value. Does it make sense? Yeah. So look at the differences. So this is the max. Okay, that is the max. Find the difference for each attribute. 1 minus 4 is 3, right? Absolute value. 6 minus 2, 4. So we have 2 attributes in this case. What is the maximum of them? 4. So that's L max. Okay. So here's another example. For example, what is the and maximum between P1 and P3? Can you do that? And max between P1 and P3. Let's do it. P1 and P3. What is it?
3.
3. Yes. Has everyone got this? Is it 3, right? You see that 0 minus 3 in absolute value is 3. 2 minus 1 is 1. So 3 is greater than 1. So we pick 3. You pick the maximum one. What is the L1 norm between P1 and P3? Also compute that. Let's see.
L1.
L1 norm. L1 norm is stipular. You compute a difference for each attribute and add them.
This,
Go back.
yeah.
So where is it? Definition is here. Or yeah, this is an example.
So the first one is L1 norm.
L1 norm. So what you do in L1 norm is you find the difference for each attribute in absolute value and add them up. So
L2. What's L2 called?
L2 is Euclidean distance.
Okay. It's 4.
Yeah, for L1 norm, for this example, the answer will be 4. And what will it be for Euclidean methods for P1 and P3? Euclidean L2 norm. What is it?
It's 13.
Square root of
13.
13 or 10.
0.
So 3 is the difference multiplied. You take the square, 3 square is 9.
That's 9.
The next attribute is
It's 1.
1. 1 square is 1.
Yeah.
9 plus 1 is 10. Square root of 10. Whatever its value is. Does it make sense? Okay. So I showed how it is done for L-infinity norm, L2 norm, which is the Euclidean distance, and also L1. Question?
Can you write down one example?
Yeah, it is in the previous
Yeah.
case. Here. Even on P2, communicate.
But in this table, in page 54, there are P1, P2, P3, P4.
Yes.
But in the example, there is only 2. L1.
Yeah, but I said that find the distance between P1 and P3. Okay. So when I say that P1 and P3, so you need to find here, right? So it's here, it's here, it's here. So that's what you are finding in the table. So that's exactly one value. You can use L1 difference, L2, L infinity.
So for P3,
Yes.
in the first column there is also P3. So why we take 3, not 0?
Say your question here.
Here it's like for P3 it is 3, but in that table there is P3 in the heading, also P3 in the left.
Yeah. So we are measuring, this is distance matrix, right? So you are measuring distance of one value against another value. So usually distance matrices are square matrices. You find the distance of each value. For example, you find the distance of P1 to all other points. You find distance of P1 to P1, P1 to P2, P1 to P3, P1 to P4.
Okay.
Again, you do the same thing for P2. Find the distances from P2 to P1, P2 to P2, P2 to P3, and P2 to P4. You do it for every possible pair.
So my understanding is if you tell L1, find the distance L1, P2, P3, then I take 2 in the table, like.
What is your question?
The thing,
Are you talking about this one?
yes. So if you tell A from L1 table,
Yeah.
this case from between P2 and P3, then I take 2.
P2 and P3, let me say P2, yeah, the distance 2.
And in P4, it will be 0.
But this is the distance matrix, okay? If the diagonals were 1, we were going to call it a similarity matrix. So that's the difference. So in distance matrices, diagonals will be 0. In similarity matrices, the diagonals will be 1. For similarity is between 0 and 1, the value is maximum when the object is very similar, or exactly the same. Does it make sense? I talked about this some time ago.
Yeah. Say that last part again. Like,
So for a similarity matrix,
similarity.
the diagonals will be 1. Questions? Any other questions?
And in which case it will be 0.
For distance, this matrix, when the object is exactly the same as itself, it's going to be 0. For similarity matrices, when the objects are totally different, the similarity is 0. Let me move this part a little bit faster. This just shows how the variables change. This is everywhere normal. I'm not going to get into this one. How variance change with respect to each other. Okay, this shows the covariance. So this is another measure. This is where I would like to get into. This is called Mahalanobis distance. So in the test, I ask you to spell this. If you get the spelling problem, you get it.
I'm just gonna write it out. So,
So I give the formula. What is it? Okay. Here's the. I'm just kidding you. Expect such a question, right? The thing is, you need to get the logic. Okay. You can always write that function. Okay, if someone gives this the formula, you can implement and you can, but you should get the logic behind it. Why do you want to use Mahalanobis distance instead of Euclidean? So I am going to make the next slide. It's going to let me explain formula. So if you look at the distribution of data, but this is more related to distribution of data. It looks like the data is around this line. It goes through this line, mostly. Okay. There's a line that goes through like this, so the data is centered around that line, goes through the diagonal, right? You'll see that. You see that? Okay. So if the data is closer to that line, we assume that they are conformant. So they are, in terms of what you see is, it's not an outlier because the data is around that line. But whenever data goes far from the line, then it means that this data is a little bit different from the rest of the data. So in this sense, just as an explanation, if you look at this A and C, okay, they are around that line that I mentioned. Okay, if I draw it, the line will be something like this. Okay, this is the line that the data is distributed on. Okay, this is the line. They are all around this. The line is not something like this, right? The line is the one that I drew previously. So if the data is close to that line, we are going to assume that they are close to each other. If the data goes far from the line, then we are going to think that they are a little bit different. So in this one, points A and C, okay, there are points A and C. They are actually a little bit far, right? They are a little bit far compared to this between A and B. But A and C are close to the line. Because of that, they should be considered similar. Which line? The one that I drew, the first line I drew here, this one. It's the line. I try to do a regression, okay? If you know what regression is, I try to do line fitting. If I just need to draw a linear line, probably this line that I have drawn will be the line. So they are more conformant, so they are more general, that one. Okay? But if you look at A and B is a little bit far from the line, right? So it is not consistent with the rest of the data. Because of that, although the distance is smaller, the actual distance is considered larger. So Mahalanobis distance measures this. If the data is consistent with the general trend, yes. For example, let's say you are buying a car, you look at the different years for the car. But as the year is getting newer and newer, the car should be expensive. But whenever you find a car that is a little bit old, and the car is expensive, really expensive, then that difference is a problem. For example, let me just give you an example. Let's say there is a 2020 car, which is 25K, okay? And there is a 2010 car, which is 15K. Okay, I just make up, okay? So these numbers are related to each other. I don't see a problem here. But when I see a 2005 car with 16K, then okay, this data, although it is closer to 2010 in terms of value, which is just $1,000 difference between them, it's something we do not consider that car is very similar to that car. There is something, so there is something wrong over there. Okay, that's what I don't know. Does it make sense? Yeah. This is my interpretation of Mahalanobis distance. How does it do it? It uses covariance matrix. Basically, covariance matrix checks how each attribute is distributed with respect to other attributes. Right? The diagonal will be variance, the other values will be covariance. So as an example, if we have A as 0.5, B as 0.1, C as 1.5, 1.5, okay? Then when you compute the Mahalanobis distance for this covariance matrix, so the formula is like this: P minus Q inverse of covariance matrix, then P minus Q transpose. So that's the formula. Okay. So that's the formula. So when we do this, you look at that B01 should be close to A by just looking at these values. Okay. So 0.1 is equal to 0.5, 0.5. But if you look at Mahalanobis distance, C is closer to A. Okay, that is what it is. So it uses this one. To see the computation, first you need to compute the inverse of this covariance matrix. This is what we get when you compute the inverse of this covariance matrix. Then you look at the difference, basically, for each dimension. 0.5 negative 0.5 here, and then 0.5 negative 0.5 here, transpose. For Mahalanobis, A6 negative 1, and then negative 1 here. So when you compute this, you get 4 for this one, and then 5 for the first one. Does it make sense? Okay. So if you see a data that is out of the trend, it's going to have more distance to data. Although, the values could be similar. But it is out of the trend. And that's what it measures. Similarities, I already went over this. If object is exactly the same, similarity is 1. Okay. And typically similarity for the range of similarity is 0 to 1. if typically for similarities, we also expect symmetry. The similarity between P and Q is the same as similarity of Q and P, typically. Okay.
That is one.
Is it?
Like you people like the similarity is one. Object is maximum similarity is one.
The one is the same object. This one is exactly the same object.
So S2 equal one or L.
What is?
S parenthesis P and Q equal one or L.
Or
It's one or L.
it's one.
It's like L. So
Yeah, and so there will be non-symmetric similarity measure. I'm just going to give one example. For example, sometimes we try to classify handwritten characters, and we want to recognize A versus B. Okay. It could be very similar based on someone's writing. For example, sometimes the actual letter is 8, but it is classified as B 20 times in this case. If you look at here, 8 is classified as B 20 times, but B is classified as 8 15 times. Okay, so you know that the system is able to recognize B better than A. So the similarity is not of B to 8. The similarity of B to 8 is not the same as 8 to B. Probably we are a little bit more careful when writing B, but we are not very careful when we write A. Okay, but that's what it means. It's a simple similarity. But to make it symmetric, you can just take the average of the similarities that is going to be symmetric. Another one is simple matching coefficient. Okay, these are all important. Okay, so I think there was a question. And what type of questions do you expect in the test? I usually ask problems. Okay, most of the time you are going to get problems. Okay? I don't ask coding in the test, but just problems. So one of them is this is for binary vectors. So let's start with binary vectors. Just to explain, so you have a vector P1 and vector P2. Okay. Vector P1 is 1, 0, 0, 1, 1, 0, 1, 0. Okay. The other one is 0, 1, 0, 1, 0, 0, 0, 1. I have two vectors. But this is a question. That's what I mean by binary vector. Binary vector is where values are either 1 or 0. Okay. So two techniques. One of them is called simple matching coefficient. The other one is called Jaccard coefficient. But they all depend on the same thing. Okay. I need to compute M00, M01, M10, M11. Okay. So I am going to just count them. So what I'm going to do is I look at each column. Okay. I have 1, 0. Just write 1, 0. I have 0, 1. Okay. 0, 1. 0, 0. 1, 1. 1, 0. 0, 0. 1, 0. And I have 0, 1. Okay. Did you see that? Did you get what I did? I put 1, 0. 0, 1. 0, 0. 1, 1. 1, 0. 0, 0. 1, 0. 0, 1. That's what I put here. Now, what I'm going to do next is I am going to count how many times they appear. Okay. M00, M01, M10, M11. How many zeros do I have?
2.
2. How many 01s do I have?
2.
2. How many 10s do you have? 3. How many 11s do I have? 1. Okay. So this is what I get. Once I get this, this is the simple matching coefficients formula. Okay. SMC. Let's compute this one. In the numerator, I have the matching ones, M00 and M11. Okay. So M00 is 2, M11 is 1. 2 plus 1. In the denominator, I have all. So it's actually the number of columns, but I'm going to add them up anyway. 2 plus 2 plus 3 plus 1. Okay. 3 over 8. That's simple matching coefficient. So this means that 3 out of 8 columns match. 3 out of 8 columns match. That's what it means. The other one is called Jacquard. Okay, so it's again the same based on the same formula. M11 here, M011011. So it ignores M00. Okay. So it means that for this one, this is very important. We use Jacquard in many applications. Okay. So if two objects, so for example, 0 means whether that characteristic appears or not. Okay, something like that. So if it appears, it's 1. If it doesn't appear, it's 0. You can assume like that. You take a course 1. If you don't take a course, it is 0. Okay. This Jacquard says that. This is the logic behind it. In many cases, what we don't have, what the object doesn't have, will be many. But what the object has matters. Okay. For example, for you, if we consider all the courses that are offered at university, let's say we are offering 1,000 courses per semester, and you are taking roughly 3-4 courses. What matters for you is the courses that you take, not the courses you don't take. If you just look at the courses you don't take, you are all the same. Every student is almost the same. They are 99.7 similar to each other. Just count the courses that you take to measure the similarity between students. Here's an example. Does it make sense? So for this one, in the numerator, I am going to have M111. In the denominator, I am going to have 2 plus 3 plus 1, 1 over 6. That's actually what matters. So if one has a characteristic, the other one doesn't have a characteristic, then that's a difference, right? Plus, if both of them has the same property, that's also something that we should consider. That's Jacquard. Jacquard makes sense for asymmetric attributes, where one value is more common than the others. For example, in typical databases, zeros will be more common than ones. Then in that case, we are going to use Jacquard. Does it make sense?
There is 2 twice, so we take only 2. We have 2, 2, 3, 1. So
Yeah.
2 have similarity, so we just only take 2.
I didn't get your
So
point.
in the denominator, you use 2.
Plus 3 plus 1. You only put M01, M10, M11. M00 doesn't count. You don't, if two people don't have that property, it doesn't make any sense. It doesn't mean they are the same. If you don't take the same courses, okay, let's say no one takes US government course right now. If students don't take the course, it doesn't mean that they are similar. It only makes sense when you take a course and the other one doesn't take a course, or both of you take a course. That's the time that the similarity distance makes sense.
So we exclude M00.
Zero, yes.
The reason is no one took that course.
I mean, zeros are, if you look at the course that you don't take, how many courses you don't take in the university? How many courses? 1,000, okay? So we don't compare two objects similarity based on the things that they don't have. We just look at the things they do. Okay, that's what it means.
If the value like M00 may be 4, so we also
It doesn't matter. It could be 1,000. It could be 10,000. It doesn't matter.
I thought like 2 is similar, that's why I take only 2.
No. Any other question? Okay. So this is an example, so you may check this example later. Okay. So there is another measure called cosine similarity. For distance measures, Euclidean is usually typically the default measure. Okay, if you don't know what to start with, you go with Euclidean distance. For similarity measures, we typically, if you don't know which similarity measure you just directly go with cosine. So cosine typically the default one. Whenever you see it doesn't work as expected, then you try other ones. Okay. So what is it? So cosine distance between. So this is also for non-binary vectors. It works for non-binary vectors. Cosine d1 and d2. You take the dot product, divide by the length of the vectors. That's what you do. So if you see that if d1, if it's your vector 3, 2, 0, 5, 0, 0, 2, 0, 0, and if the other vector is 1, 0, 0, 0, 0, 0, 1, 0, 2, you first find the dot product, meaning multiply each corresponding value, find the product of each corresponding attribute, 3 times 1, plus 2 times 0, plus 0 times 0, plus 5 times 0, plus 0 times 0, etc. You go up to 0 times 2. Okay, you get 5 in this case. The length is, it's like Euclidean somehow. You look at this 3 square plus 2 square plus 0 square plus 5 square plus 0 square, and you add them up and then take the square root of it. You get 6.4 for the first one. And for the other one, you do the same thing. 1 square plus 0 square plus 2 square, and then you take the square root of it, you get 2.2 something. And then cosine will be 5 divided by 6 times 481 times 2.248. You get 0.3150. But this is also used a lot. So you get the dot product, divide by the length of the vectors. This is also equivalent to the angle between the vectors. Angle between the vectors. This is extended Jacquard. Why we have this? This is just additional information. This Jacquard is for binary, okay? Binary values, either 0 and 1. So this one is for non-binary attributes. Okay, so continuous or commutative. So may work for them. This is just additional. There are additional measures to find the similarity of this, like correlation. Okay. Just to understand what correlation is, it measures the linear relationship. Okay. Let's say x is -3, 6, 0, 3, -6, and y is 1, -2, 0, -1, 2. Okay. So you realize that they are very similar. If you multiply y by minus -3, you get x. If you multiply, in this case, y by -3, you get x. So they are correlated. X and y are correlated, but correlated in the negative direction. So there's a linear relationship. Similarly, if you have 3, 0, 3, 6, 0, 3, 6, and then y as 1, 2, 0, 1, 2, they are still related, right? So if you multiply y by 3, then you get x directly. So there's a strong linear relationship. Correlation does not measure non-linear relationships. Okay. So if you look at this, you have x the same or similar, x -3, -2, -1, 0, 1, 2, 3, and y is just square 9, 4, 1, 0, 1, 4, 9. The correlation is 0. The correlation does not measure non-linear relationship. So if you look at this, this is x, this is y. So how x and y change with respect to each other. In this case, as x increases, y decreases down. So they are inversely related. So in this case, the correlation is -1. But as x increases, y also increases. So this is a perfect case, so it is 1 in this case. In general, if that's the case, you have high correlation 0.9. If that correlation decreases a little bit 0.8, and you have some some correlation, but not too strong, it's 0.5. In the worst case, you get something like a circular shape, then there is no correlation at all. Here mean we did linear relationships. Okay? I think I may skip this slide. What this says is how to consider attributes of something. We also assign weights to differences. Okay, you don't need to just take the difference, but multiply with the weight as possible. So let me give you a short break here, about 30 seconds. Any questions before I continue with the next? So I'm going to change the topic.
Okay. In this part of this many distance you showed us, it's gonna be like you will be telling us which one to use at each time, or we just have to figure it out which one's supposed to use.
So in which scenario the question?
So I'm trying to think of it like if you're assuming we have a new project to do,
Okay.
and
So it depends. So sometimes you may get it clearly, sometimes you don't get it clearly. So you should try it yourself and learn it.
Okay.
Any other question?
For Jacquard,
Yes.
for Jacquard, what will be the dominant, like the 1 value? So we divided 1 by 2 plus 3 plus 1. So 1 is M11 value. Okay. So this is my question. 1 will be the M11 value.
One is here and moment value, yes. Another question? Okay, so we are going back to K-means. Question? No. We are going back to K-means. So this was a problem. When you run K-means, you may not get perfect results all the time. So how do you solve that problem? you run k-means multiple times with different initial centroids. And hopefully you are going to get a good answer in some ways. Even if you are working with randomization at all, I mean in general, you would like to run your experiments multiple times. Just have this as a a feature for you. Don't just run it once. Maybe you got lucky. We may use sampling and use hierarchical clustering to determine initial centroids. So that's another technique. Another one is you may use more than k initial centroids and then select among these initial centroids. So let's say you are going to have k is equal to 10. It says that choose 20 instead of 10 and then pick the most separated 10 out of 20. We could do post-processing. I am going to explain how it could be done. That example. And there is something called bisecting k-means, which is not susceptible to initialization issues, but it has some other problems. So other solutions is if you find out that one cluster is too big at the end, you may split that cluster into two clusters. If there are two clusters that are very close to each other, you may consider merging those two clusters. But these are some possible solutions. This is an interesting problem. We may get empty clusters in k-means cluster. I'm going to show you with this example. So I have one case here. I have data 5, 40, 45, 50, 92, 100. And my initial centroid assume that is 5, 92, 100. Okay. These are my initial centroids. So 5 goes to 5, 40 goes to 5 or 92.
5.
5. 45 goes to 5. 50 goes to
9.
92 goes to 100 goes to here. But after this, the new centroid for the first one is
3.33.
30.
3.33.
It should be 30, right? It's just 30.
Okay, that's 19. Yeah, 1930.
Yeah, 30. Yeah.
300.
For the second one, what is the center? 71?
Yeah.
For the third one is 100.
Okay.
So if you do this, for the first, now we should again check all of them on my mind. 5 goes to 30, 40 goes to 30, 45 goes to 30, 50 goes to 30, 92 goes to 100. Right? It's a 100 goes to 100. So we have nothing in cluster. And even if you, from this point on, if you continue, you are not going to get any. So this is a a case you expect to get 3 clusters, but at the end you get less than 3. So what you could do is, whenever you observe this, and you realize that some clusters are empty, then you can do post-processing, meaning that you may find the largest cluster, you may find the point that is farthest from its center, okay, the farthest point from its center, then you could use that point as a new centroid and then reassign the points. So for example, in this case, if I look at it, 5, okay, maybe it's farthest right now, it's 25. I am going to reassign this. So I'm going to separate it. I am going to have new clusters for 40, 45, 50, and 92, 100. So I'm going to do reassign, find the new centers 5. It's going to be a new center, just sub 45, and it's going to be get 96 or something like that. Then reassign. So find the farthest point from the cluster center. The other one is choose a point from the cluster with the highest sum of squared errors. So if you remember, to measure the quality of a cluster, we look at the distances from the center. The one that has the highest distances from the center, you can choose a point from that cluster. And these steps could be separated several times. Another update is this is going to slow down the process. We could increment the centers incrementally. So you can update the centers incrementally. So this is what I am going to state. So if I go back to the previous example. So this is 5 for that like this. So 5. We have 92. We have 100, and our data is 5, 40, 45, 50, 92, 100. Okay. I'm not going to show the complete process, but just for to explain what this means is, so I put 5 here. Okay, the center is 5. Okay, there is nothing. That's the only data. The next data is 40. So when I put 40 into that cluster, I recompute the center at that instant. What is the new center now? 22.5. Okay, that's my new center. Then I add the next data, 45. 45 will go to here. And I'm going to recompute the center right there. As soon as I add a point to a cluster, I'm going to recompute it. Okay? And the new cluster will be 30. Okay. So that's my new cluster. So whenever I get 50, okay, as soon as I get put 50, I'm going to recompute my cluster. So whenever you add a point to somewhere, you are going to recompute. That's the way it's going to work. So this avoids empty cluster problem. Each assignment normally, so whenever you make an assignment, it says update 0 or 2 centroids. It means that the data might move from one cluster to another cluster. So whenever you add it to a new cluster, the centroid will change. But it's also changed the centroid of the old cluster because it's not there anymore. Okay. It's more expensive. You do recompute the cluster centroid again and again for each data. There is also order dependency. So why do I start with 40 as the next element? Maybe I should start with 50. If I start with 50 after 5, then the next center will be different, right? So there is some order dependency, but you can use some ways to change the impact. So earlier, maybe data may have lower weights, later data might have higher weights. Skip this one. Okay. So this is just for visualization, okay? To understand how k-means work. So you know how to implement k-means, but you also know how it behaves. And you should understand when it's going to fail. And you should think about what to do in those cases. So this is 4 clusters. Top left, top right, bottom left, bottom right. If you use k is equal to 4, these are the 4 clusters you are going to get. 0 rules, right? Nothing. So it's, k means it's perfect for this. If you make it 5, one of the classes will be split. In this one, bottom left cluster is split into 2. But that's the way it's going to be. So k-means has problems when clusters are of different sizes, densities, and non-globular shapes. K-means are also affected by data containing outliers. So let's look at this. These are the original points. So you see 2 small clusters on the left and right. There is a bigger cluster in the middle. If we apply k-means with k is equal to 3, this is what it's going to do. So it doesn't look at the shape, it just looks at the distances between data points. So it basically splits into 3 close points, right? 3 sets of close points. This is another example. What you see is there is a big cluster on the left, and then there are 2 small clusters on the right. But in this case, the small clusters on the right are dense. The big cluster on the left side is non-dense. Okay. They are a little bit separated. If we apply k-means with 3, it's going to consider that those dense clusters are close to each other. It's going to merge into one cluster. And the big cluster, non-dense one, will be split into 2 clusters. Okay, so do you see the limitations? It's an example for a non-globular shape. If we use k is equal to 2, what do you think will happen? Yes, that's very good. So this is what came. It doesn't look at the shape at all. It just looks at the distances between data points. But this is how, if you have some clusters of that type, so it's not going to, for k-means, these 2 points are close to each other, right? So it's going to put them into the same cluster. So it's based on distances. So how can you overcome, basically? This is not an easy, it's just a thought process. Rather than using 3 clusters, you can use more than 3 in the beginning, okay? And maybe you use 7, 8 clusters, and you think of which ones could be merged. Okay, you can think of which ones could be merged. For example, in this case, after you find this out, you may consider that the ones in the middle maybe could be merged. For this one, after you find this, so these are very dense clusters, you realize that these are non-dense areas, so you may consider non-dense clusters. Again, for this one, you can have maybe 10 clusters. So you may consider follow a path the clusters on the same path could be merged into the same cluster. This is another example. 3 bars with k is equal to 3. You didn't get bars as clusters. Why? Why the first top bar is divided into 2, bottom bar is a single cluster, the middle bar has basically has parts from 3 clusters. Any guess what's going on here?
Maybe the distance between the points at the ends is higher than the distance between them.
Yeah, that's the answer. So the answer is if the distance from here to here, although it's a bar, the distance from this point to this point is significantly high, it's significantly large compared to distance from here to here. That's why those green points go into the same cluster, but these points go, this red and green go into different clusters. Okay. So you think that it's going to work for this data set easily, but it doesn't. So when you make 6 in this way, now this gives you a hint. Now 6, you see that, realize that each bar is split into 2 clusters, right? You see that. Now you may consider merging the clusters on the same bar, but you see that there could be a solution when you increase the K. This is another example. We have 3 clots in this case. We have, you can say, a bar on the left, like number 1, number 2 in the middle, number 1 in the end. But when you say k is equal to 3, it's similar to the previous problem. The snake part or number 2 part will be composed of multiple clusters because of the distances. Okay. When you make k is equal to 6, in this case, it didn't even work right now because the left one still we don't get the proper one. This is ring, 2 rings. So when you ask the system cluster, what you want is each ring is a single cluster. But because of the distances, each ring is split into 2. Normally, you expect this ring to be 1 cluster. But because of the distances, this distance means that this distance from here to here is less than from the distance from here to here. With k is equal to 3, this is what you get. This is an example for density. Okay. Every point is cluster. This k is equal to 3, this is what happens. This is a weak link, meaning that it still considers, it uses the data which could be considered as noise, or they are classified as well. That's all. Questions? Does it make sense?
You expect us to use this visualization for assignment because I don't think I really know what's going on behind that case. So.
Yeah, that's what we do is typically for visualization purposes. we need to use PCA. You need to have two dimensions. You cannot visualize more than two dimensions, right? So you can use three dimensions, not more than three. We need to use PCA to get an idea. And there's another method called Tisney. So these are typical two methods we use to visualize data with many dimensions. That's what you can do. You could visualize by these methods. I recommend you to visualize PCA with two components or Tisney. There is something called bisecting k-means. In the past, I asked questions about this in the assignments, in the exams, in the comprehensive exam. Okay, so you may get questions like that. It is very simple. It's not complex, but you need to know what k-means is. So what it does is, I'm just going to make a random example like this. So you apply original data, the k-means algorithm with k is equal to 2. You apply k-means with k is equal to 2. That's what you do. Okay. As an example, when I do this, I get this one. I get this one. As an example. Okay. So among these clusters so far, I have two clusters right now. Which one is the worst cluster? Okay. What I mean by worst cluster means you can add up the distances of data to the centers. The one that has the highest sum of squared errors. Or the one in terms of visually the larger cluster. Okay, visually it's the larger cluster, but quantitatively it's the cluster which has the highest sum of squared errors. You apply again k-means only on that cluster with k is equal to 2. Okay. So what I do is, for this one, for this cluster you see here, I apply k is equal to 2. I get this one. I get this one. So I get 1, 2, and 3 clusters. You see that, right? Now I have 3 clusters. Which one has the highest sum of squared errors? I pick that cluster, apply k-means 2. With k-means with k is equal to 2. I get this one, and then maybe this one. Now I get 4 clusters. Now it depends on where to stop. So if k is 5, I need to do one more step. So among these 4 clusters, which one is the worst cluster or highest sum of squared errors? The middle one, okay. So again, we split into this one and this one. So now I have 5 clusters. So this is bisecting k-means. Right? So it's not very complex. So there are 2 steps here, or main steps are you apply k-means with k is equal to 2 all the time. You need to find out the cluster that has the highest SSE, sum of squared errors, and apply k-means with k is equal to 2 on that one until you get k clusters. Because of this logic, this is also called hierarchical clustering. So if I draw this like put everything into one cluster like this, so you see that this point belongs to this cluster. Let me put here A, B, okay. Let me call this as B1, B2, okay. There is, let me call this C1, C2. Let me call this D1, D2. Okay. A point here belongs to D2, belongs to B, and belongs to main cluster. Okay, so it has three belongings. It belongs to D2, this X. It belongs to this B1. Okay, so this X belongs to first B2, then it belongs to B1, then it belongs to B, and it belongs to main cluster. Okay. So it has multiple belongings. So you can be hierarchical cluster in this way. Why is it important? For example, I mentioned this very early, I think maybe 1 week ago, about on Monday. There is a concept hierarchy. Okay? For example, you want to cluster items that are bold. Okay? You may categorize data items, eggs, milk. Under milk, you could have 2%, 1% fat rate. You could see that kind of hierarchical organization. Or from time to time, for example, when we analyze computer network attacks, there are categories of attacks. Okay, you can have hierarchy of attacking techniques. Okay, so for that purpose, this type of hierarchical is also could also be used for that purpose. Or in animal kingdom or in plant kingdom, there are hierarchy of families for that purpose, and you don't have this type of technique could also be used. This is an example of how bisecting k-means look like. So when I start with this, with 2, the right 4 clusters is one cluster, the left 6 clusters is one cluster. Okay, which cluster is the worst one right now? That one. So we are going to split that into 2 clusters. So if I do that, it's going to have this type of sequence. Okay. So right now, which one is the worst cluster? Either the rightmost or the middle one. So it's going to pick one of those. I don't know which one it's going to pick in this case. It pick the middle one. It's like this. Now you know that the rightmost is the worst cluster. It's going to split that into 2. So it's in this way, up and bottom. Then it's going to pick any of those. It pick the right from the right side, so it pick into 2. And that one, the leftmost, and second over there. So you could get a similar clustering result as well. So there are many k-means algorithms. The usual algorithm change based on the initial selection of the k-means, distance measures that are used. For example, instead of using Euclidean distance, you could use Mahalanobis distance, so you are going to get different results. Okay. There is online k-means algorithm. This is a type of incremental. Normally, when you compute a cluster center, you first assign all data to a cluster, then take the average, right? So this is usually the batch k-means. That's what it is in this case. But online k-means is something like incremental. So whenever you add a data to a cluster, it changes the cluster center a little bit. Not completely, but a little bit. So if you look at this formula, this is the distance to the cluster center. You multiply with the coefficient. Whenever you add x to a centroid, to a cluster, it's going to move the cluster centroid towards x, little bit. Okay. You can use a small number depending on the size of your data. There is one more. I'm going to maybe explain this later on. Let me read it through next time. Let's stop here. What this is actually, it doesn't go with k directly. Whenever distance of a point to a cluster center is greater than a value threshold. For example, your threshold is 20. Whenever you have a new point, it is farther than 20 to any cluster. It says that create a new cluster for that point. You don't specify the number of clusters, but you specify how close or how far the cluster should be. That's adaptive resonance theory, and I can go over it next class. But I'm going to come and cover on Wednesday. Okay, that's what's going to.
So it should be kind of binning what she just explained now.
Say again.
Would that just be like kind of binning? Like you're gonna bin because of you set the threshold for it?
Not binning. For example, in the assignment, you provide k is equal to 3, k is equal to 5, right?
Yeah, I'm talking about the threshold.
Yeah, threshold.
The row.
In this one, you don't have the